All right, class, so this explanation video is for the second question on this extra ice table practice. And this question, it's a really great question. We're gonna have to use the quadratic formula on this question. So it's good practice. You definitely should be able to use the quadratic formula. But again, this is not something that I would typically ask you to do on an exam or something like that. But it is something that I feel like you should be able to do. So let's go ahead and get into this one. This one's a lot more complicated, so it's gonna be a little bit of a longer video. But stick with it, and this is something that you should be able to do. I do expect this out of you guys. Okay. So in this question, what we're asked to do is calculate equilibrium concentrations of all the gases. So that's my question here, equilibrium concentrations of all the gases. If initially there is 14.6 grams of NH3 placed in a 4-liter vessel. So that's my initial setup. And then in my equilibrium reaction here, I've got a Kc value that's given. The Kc value for that is 0.83. So we'll need to use that in order to solve for the number of moles or concentrations at equilibrium. So the first thing I'm going to do is convert this grams of NH3 into moles, and then convert that into molarity to figure out my initial concentrations, right? So in my ice table, I'm going to have an initial concentration here. These will be 0 since we're just starting with that NH3. So let's go ahead and do that. 14.6 grams times 1 mole over 17.04 grams. That gives me a number of moles of 0.857 moles, and that's my moles of NH3. Then converting that into molarity, 0.857 moles divided by 4.0 liters in this case is going to give me a starting molarity of 0.214 molar NH3. So that's what's going to go right over here, 0.214 molar. And again, it's just a good idea to use concentrations, to use molarities in your ice tables. You can use number of moles, but that just becomes a little bit tricky when we're dealing with our Kc, right? Because remember that our Kc is in terms of molarities, in terms of concentration. My change line here is going to be minus 2x plus x, and then plus 3x. So I don't know if we've seen this yet, but since this coefficient is 3, that means that it's going to be plus 3x. And then at equilibrium, 0.214 minus 2x, this is the expression. This is going to tell us mathematically how much NH3 I have at equilibrium. I'm going to have x molarity of N2, and then I'm going to have 3x molarity of H2. So it's a 1 to 3 mole to mole ratio, so this would make sense, right? Whenever we make N2, we're going to make 3 times as much H2. So this is my expression for equilibrium. And then I'm going to apply that to my Kc, right? So I know that Kc is equal to 0.83. It's my value for Kc. And then that's going to be equal to my concentration of N2, which is going to be x, times my concentration of H2 raised to the 3rd power, right? So this Kc, it's going to be this concentration of H2 raised to the 3rd power because that's what the coefficient is. I'm going to divide that by 0.214 minus 2x, and that's going to be squared, again, because of that coefficient of 2 there. So now I need to solve this for x, and this is where that whole math, algebra, quadratic formula, all of that stuff's going to come into play. So I'm going to walk through this slowly and show you sort of my strategy for doing something like this. And then if you want to skip ahead to the end just to see what the right answer is, definitely feel free to do that. But I think it's a good practice. It's something that we should be able to do. The first thing that I'm going to do is I'm going to simplify this side. I'm going to combine these terms. And one thing that's really sort of tricky, I guess, and a common mistake is dealing with this 3x to the 3rd power. So this top portion here, that's going to actually simplify to 27x to the 4th. And then down here, we're going to have 0.214 minus 2x squared. So this 3 to the 3rd power, that's where the 27 comes from, and then x times x to the 3rd is going to be x to the 4th, and that's going to equal 0.83. The next thing that I'm going to do is I notice that I can sort of take the square root of both sides here and simplify things a little bit. So I'm going to go ahead and do that. So we'll just write it in like this, take the square root here, take the square root here, and then now we're going to want to simplify that. So I think what I'll do is I'll flip this over, and we'll just start with a clean sheet of paper to go through the rest of this math. So I'll just move this up, and we'll see where we're starting at here. So the next thing that we're going to see is, let's do it this way. 0.83, and we can also write that to the 1/2 power. That means the same thing as what we're seeing here. Is going to be equal to 27 to the 1/2 power times x squared, so x to the 4th square root of that, and then all of this is going to simplify just to 0.214 minus 2x. It gets rid of that squared there. So now this is where we're at this point in time. So then I'm going to sort of start grouping things together and trying to simplify this out. So the next thing I would do is I would bring this 27 to the 1/2 down over here. So essentially dividing both sides by 27 to the 1/2. 0.83 to the 1/2, and again that's the same thing as square root, equals x squared, and then we've got 0.214 minus 2x. Now I'm going to get an actual value for this term right here. So calculate this out, and what you're going to end up with is 0.175. So if you actually plug that into your calculator, that's what you'll end up with, 0.175. We're going to say that that's equal to x squared, again, over 0.214 minus 2x. And then what I do is I sort of bring this piece up. I'd bring this piece over here, 0.175, 214 minus 2x. A lot of math here, a lot of writing everything out, equals x squared. Then I'm going to, and the last step I sort of skipped ahead here, but I'm going to multiply this out and then bring everything back over to this other side just so I have this x squared over here. So all of this again would simplify to 0 equals x squared plus 0.351 times x minus 0.0375. So this gets me ready to use the quadratic formula to solve this using the quadratic formula. This is the form you need to simplify it in. And this is a lot of math, right? This is a lot of algebra to get to this point, right? So we started way up here where we've got this KC expression, we've got our x values, and then all of this to get to this point here is just really algebra, right? And we need to be able to do that. Once we're at this point right here, we can use the quadratic formula to solve for x. I'm not going to show that, but suffice it to say, we're going to get two terms for x, two possible values, negative 0.437. That's obviously not going to be a valid answer for us, or 0.0858. Oops, 858. That's going to be the one that we're looking for here. Sorry that looks so shitty. 0.858. There we go. And this is going to be the term that we choose, because this term minus 0.437, it gives us nonsensical answers, right? If we go back to our ICE table, the x value really needs to be positive, right? A negative x value doesn't mean that we have negative n2, which does not really make any sense. So our x value needs to be positive. So this 0.0858, that is our x value. We're almost there. So what I'm going to do here is I'm going to rewrite my equilibrium line, from above. 2NH3 is in equilibrium with N2 plus 3H2, and my term here at equilibrium, let's see if I can squish this down, is going to be 0.214 minus 2x. This is going to be x, and this is going to be 3x. So if this is my x value, right, 0.0858, I can use that to solve for those equilibrium concentrations. And if I do that, then I get 0.0424 as my concentration of NH3. This is just going to be 0.0858. And then for hydrogen, it's going to be 3 times that, and that equals 0.2574. So these are my equilibrium concentrations. What do these represent, right? These represent the equilibrium concentrations of NH3, of N2, and of H2 once we get to equilibrium. All right. So obviously it's an involved problem, but if you're struggling with this still, this is something that you definitely need to get a handle on. You need to be able to do a problem like this, for this General Chemistry 3 course that we're going to be taking off on. All right.